Welcome to the Explainer. You know that spicy kick you get from cinnamon? Or how something like nylon can be so incredibly strong? Well, the secret to both is a tiny but super powerful group of atoms called the carbonyl group. It's the absolute star of the show in aldehydes, ketones, and carboxylic acids, which are huge topics in organic chemistry. So let's break it all down and get you completely prepped for your exams.
Okay, here's our game plan for today. We're going to kick things off with the basics of what a carbonyl even is. Then we'll dive into the rivalry between aldehydes and ketones, figure out some clever ways to tell them apart, and then meet their acidic cousin, the carboxylic acids. We'll also spotlight a really key reaction you need to know, and then see how all this amazing chemistry comes together to make everyday stuff like nylon. So let's start right at the heart of it all, the carbonyl group itself. This is the one feature that connects every single compound we're talking about today, and really getting a handle on it is the key to understanding everything else. This right here, the C double bond O, is what it's all about. I mean, this is a powerhouse of a functional group. You find it everywhere, from the vanillin that makes your food taste great to the plastics and fabrics you're probably using right now. And the real secret to why it's so versatile, it all comes down to its unique structure and reactivity. So why is this group so reactive? Well, it really boils down to two things: its flat shape and its polar bond. You see, oxygen is a real electron hog, so it's constantly pulling electron density away from that carbon atom. This leaves the carbon with a partial positive charge, which basically turns it into a magnet for nucleophiles. Those are electron-rich molecules that are always looking for a positive charge to attack. This idea is the absolute foundation of all carbonyl chemistry. Okay, now let's meet the two main branches of the carbonyl family: aldehydes and ketones. At first glance, they look super similar, but there's a tiny difference in their structure that creates a massive difference in how they behave. And here it is, the key difference. Aldehydes have at least one hydrogen atom attached directly to that carbonyl carbon. Ketones, on the other hand, have two carbon-based groups attached. Now, that might seem like a really small detail, but trust me, it has a huge impact on their reactivity. All right, highlighter out, this is a big one for exams. Seriously, you need to know this. We're putting aldehydes and ketones head-to-head in a reactivity showdown. So let's dig into the two key factors that decide which one comes out on top. This chart breaks it down perfectly. First, you've got the electronic effect. Alkyl groups, those carbon groups, are electron donating, meaning they push electron density towards the carbonyl carbon, making it less positive. Since ketones have two of these groups, their carbon is just less of a target for nucleophiles. Second, there's the steric effect, which is really just about crowding. An aldehyde's tiny little hydrogen atom leaves a wide open path for a nucleophile to attack, while a ketone's two bulkier groups kind of get in the way and block the attack. And the verdict is in. Aldehydes win the reactivity race, hands down. Thanks to both electronic and steric factors, they are way more open to nucleophilic attack than ketones are. If you remember one thing from this section for your exams, make it this: aldehydes are the more reactive of the two. This little three-step dance is the basic playbook for reactions with both aldehydes and ketones. First, an electron-rich nucleophile attacks that electron-poor carbon. This breaks the double bond and shoves the electrons up onto the oxygen. That creates a negatively charged intermediate, which then quickly grabs a proton from the solution to form the final neutral product. This is a fundamental mechanism you've got to know. Now, this difference in reactivity isn't just a fun fact. It actually gives us a really clever way to tell aldehydes and ketones apart in the lab. So let's say you've got an unknown sample. How do you figure out what it is? Well, the trick is to use a reaction that's picky, a reaction that only the more reactive compound, the aldehyde, will actually go through. We can do this with what are called mild oxidizing agents, because it's just way, way easier to oxidize an aldehyde than it is to oxidize a ketone. And that brings us to our special tool for the job, the Tollens test. You'll also hear it called the silver mirror test. The reagent itself is a mild oxidizing agent that's just strong enough to react with an aldehyde, but it'll completely ignore a ketone. It's the perfect diagnostic tool. And the visual cue here is honestly unmistakable. It's pretty cool. If you see a beautiful, shiny silver mirror form on the inside of your test tube, you can be 100% sure you've got an aldehyde. If the solution just stays clear, you're looking at a ketone. It's that simple. So what's actually going on here chemically? Well, the aldehyde is getting oxidized into what's called a carboxylate anion. At the same time, the silver ions that are in the reagent get reduced to solid metallic silver. That silver then coats the inside of the glass and voila, you get that amazing mirror effect. Okay, We've covered aldehydes and ketones pretty well. Now it's time to meet the third major member of the carbonyl family, the carboxylic acids. And these guys have a totally unique personality, all thanks to a hydroxyl group that's attached to the carbonyl carbon. So this combination of a carbonyl and a hydroxyl group gets its own special name, a carboxyl group. And that extra OH group is a complete game changer. It gives carboxylic acids their most famous property, their acidity. You know, hydrogen bonding is a huge deal for carboxylic acids. It's like their superpower. They can form these really stable pairs called dimers, which means it takes a ton of energy to pull them apart. That gives them really high boiling points. And of course, their defining feature is that they're acids. They can donate a proton. Speaking of unique properties, let's talk about a classic reaction that is an absolute favorite on exams. It has a pretty intense name, the Hell-Volhard-Zelinsky reaction, or HVZ for short. It's a really powerful tool that's specific just to carboxylic acids. The whole trick of the HVZ reaction is that it lets us stick a halogen atom, like bromine or chlorine, onto the alpha carbon. That's the carbon right next door to the carboxylic group. This is a super useful move in organic synthesis, but it only works if that carboxylic acid has at least one alpha hydrogen to begin with. And look, this table is basically your cheat sheet for the exam. It's got everything you need to know. Your reactant has to have an alpha hydrogen. You use a halogen like bromine plus a phosphorus catalyst, and your product is an alpha halocarboxylic acid. You'll definitely want to have this one memorized. Okay, to wrap this all up, let's see how this chemistry is actually used to make one of the most important materials in the world, nylon. This is where all the theory really hits the real world. So here's why all this stuff matters so much. We start with this stuff called Ka oil, which has the ketone cyclohexanone in it. Then we oxidize it, which actually breaks the ring open and forms adipic acid, which is a dicarboxylic acid. That adipic acid is one of the two main building blocks for making nylon 6,6, a material that's in everything from your clothes to your car. It's just a fantastic example of ketone and carboxylic acid chemistry in action. So as you're reviewing all of these concepts, here's a great question to chew on. It really gets to the core of structure, stability, and reactivity. I'll give you a hint. Think about the stability of the conjugate base that forms in each case. It's not just about how many resonance structures you can draw, but how stable those structures actually are. It's a great way to really lock in your understanding. Thanks for joining us on The Explainer.